Okay, on section 12.2, the second derivative. The first thing we want to look at is what does the first derivative of a function represent? So if you remember, that actually represents when a function is increasing or decreasing, basically the slope of a function. So look at this example here. Figure 12.23 shows the prices of two different stocks over a period of months. Both stocks are worth $5 per share at the beginning and are continually increasing in price. Which one is the better investment? So notice that the A line there is in blue, the B line is in red. Which do you think would be a better long-term investment? Remember, this is a stock that you purchase, so you want the price to go up. So you're right, it is easy to see from the graph that stock B is the better long-term investment. In real life, however, you only see part of the graph, like the past performance of stock. You don't really know what it will predict in the future. So, and notice how like both of them are increasing. They both started at the same amount, but what makes it different is the rate of increase. So how can we determine the rate that a function is increasing or decreasing? Basically, what we need to know, or we need to find, is the derivative of the derivative. So we're going to be looking for the second derivative, because how fast something rises or falls is important in a lot of different situations. In mathematical terms, if the price of the stock in month X is f of x, then the derivative of f of x tells you when the price is increasing or decreasing. The rate of increase or decrease of that derivative function is given by its derivative. In other words, the rate of the stock price is increasing or decreasing is given by the derivative of the price function. So in this whole section, we are looking at the second derivatives. All of these notations represent the second derivative. You can even do the third derivative, fourth derivative, and so forth, which we'll look at in this particular lesson. So, kind of on the back. Example 1, find the second derivative of the given functions. So in example 1, part A, to find the second derivative, the very first thing you have to do is find the first derivative. So let's see. The derivative of this one would be 24x squared minus 18x plus 6. And then we find the derivative of that. So let's see, that's our second derivative. Be sure and do your notations correctly. This would be 48x minus 18. So sometimes it's pretty straightforward and easy, like that one. Sometimes not so much. Part B is a little bit more detailed. So let's look at that one. If we do the first derivative here, remember it's low d high minus high and then d low over low squared. And then we've got to clean that up. And I don't need to narrate you through this. I think you can get this far yourself. Okay, so that's our first derivative. So now we've got to take the derivative of that for our second derivative. This is why I left all this space right here on this page, y'all. Okay, so second derivative would be, why did I put a 6 right there? That's a 2. Good thing you found it before you guys did, right? Okay, so low d high minus high and then d low and over low squared. Can you see that? Yeah, okay. So if we clean this up, oh wow, that goes to 0. So negative negative makes it positive. That's 60 times 3x minus 1 over 3x minus 1 to the fourth, which if we clean that up, that gives me 60 over 3x minus 1 to the third power. And then on part C, let's see, this has x times e to the x, so that is our product rule there. So first derivative, that would be first one times the derivative of the second plus the second times the derivative of the first. So that would give us x e to the x plus e to the x. That's our first derivative. Second derivative is the derivative of that. So that is going to be first one times derivative of the second plus second times the derivative of the first. That's for like this chunk. Okay, that's where that came from. And then just that, because the derivative of e to the x is e to the x. So that means we have x e to the x plus 2 e to the x. And you can leave it like that. Sometimes you see it where you factor out the GCF. Sometimes you see it like this. Either way would be fine with me. Okay, so example 2. Suppose that over a 10-month period, the prices of stock A is given by this particular function, and the price of stock B is given by the g of x function. When are stocks A and B increasing in price? So basically we need to find the derivative of each one of those and then pull our information from there. So in part A, let's see, the derivative of the first one, that would be 1/2 x to the negative 1/2. And if I clean that up, that gives me 1/2 x to the 1/2, or square root of x I could have put. On the derivative of the g of x function, let's see, that would be 0.1 times the 3/2 x to the 1/2. And if you multiply that, I believe you get this. I know you guys will check it for me and let me know if that's not the case. So at this point, we're looking for critical values. Critical numbers. So I know on this one that, well, you know what? I'm going to write this as square root because that's going to help me see it better. Because remember, this is the square root of x. And I know that x has got to be greater than 0 because of the domain restrictions on that. It can't be 0 because it's on the denominator. It's under the square root. It's got to be greater than 0. So I know it's increasing greater than 0. The other one, basically it's the same thing, right? Because this is square root of x. Might be easier for you to see like that. So I know x has to be greater than 0 here. So both of them are increasing. X is greater than 0. Both are increasing for x is greater than 0. All right, so part B. At what rate are these stocks prices increasing in the 10th month? So we're talking about rate here, the rate that they're increasing. So I need the second derivative at that point. So the second derivative of this one, let's see, that would be, I'm going to go back and look at it at this part. So that would be 1/2 times negative 1/2 x to the negative 3/2. So cleaning that up, that gives me negative 1/4. And the x to the 3/2 would be on the bottom. For the second derivative for the g of x function, that would be, let's see, if I do the math on that, I think it's 0.75 x to the negative 1/2. So if I plug in 10, because we want the 10th month, probably should have double checked these numbers after the last one, right? But I'm going to just let you guys do that. Okay, so if I plug in 10, I think I get these numbers. So notice that this negative means it's increasing at a decreasing rate. So I'm going to write price of stock A is increasing at a decreasing rate at 10 months, or in the 10 months. In the 10th month. This one's a positive. So the price of stock B is increasing at an increasing rate. Price of stock B is increasing at an increasing rate at 10 months. So which one is the better investment? Stock B. This one would be better investment because it's both of them are still increasing, but this is increasing at an increasing rate. So it's gaining more, and that's what you want. Now, although example 2 is actually much simpler than real life, believe it or not, second derivatives are actually used by investors also. So the second derivative approach involves looking at such things as profit warnings, analysis earning estimates, equipment orders, including cancellations for signs of the downward momentum slowing. So it's used a lot like on Wall Street and things like that. So, it's important to do this. If you plan on going to business, having money one day, you need to know how to make good investments, and using these math skills could potentially help you earn money in the future. The second derivative also plays a role in the physics of a moving article. If a function describes the position of a moving object along a straight line at time t, then the first derivative gives us the velocity. The rate of change of velocity is called acceleration. So our second derivative gives us our acceleration. So you need to know what those are. And there's a little formula down here, but velocity is first derivative. Acceleration is the second derivative. So on a test or whatever, or in a word problem, if they're asking you for velocity, you need to know do the first derivative. Acceleration, you do the second derivative. Now on the next example, example 3, says suppose that an object is moving along a straight line with its position in feet at time t in seconds given by that particular function there. Find the velocity for part A, find the acceleration for part B, and then answer part C. Find when the object stops, its velocity is 0. For t greater than or equal to 0, when does that occur? So first one, find the velocity. That means our velocity, remember, is our first derivative. So that is 3t squared minus 4t minus 7. On part B, find the acceleration. Well, the acceleration is the velocity, no, the derivative of the velocity, which is basically the second derivative of the thing there. So that's 6t minus 4. So those are pretty easy. I like those. Now part C, when the object stops, its velocity is 0. When does that occur? So if we want velocity equal to 0, so I take my velocity, set that equal to 0, and then solve it. So let's see. This one should factor. I think it does. 3t minus 7t plus 1. Would that work? Because that gives us plus 3t minus 7t. Yeah, that works. So using our zero product property, I know t is 7/3 or t is -1. And of course, we're talking about time here. That one is extraneous. So the object will stop in 7/3 seconds. Seven-thirds. Sounds odd to think of time as putting it as 7/3, doesn't it? You could write it as a decimal if you like, or as a mixed number, 2 1/3 seconds, or 2.3 with a bar seconds. Kind of depends, like on Math Excel, what they would ask you for on those. We will finish the notes on the next video.